Good morning, everybody. Hope everybody's doing all right. All right, so we're going to finish up chapter 8 today as best we can. It's going to be a packed day. Then Monday, we'll start chapter 9. So we're finishing up, or not Monday, Tuesday, next week. First day next week. So we'll start chapter 9. We'll have finished chapter 8, so that should tell you something. And then we have an exam next Thursday, so it's a week away. And so we're on track to have everything covered for the exam next week. Now, I'm not going to be here over the weekend, so there's not going to be a review session on the weekend. We'll schedule some time during the week. In the evening, I'll try to schedule a couple of time slots. On probably Tuesday evening and Wednesday evening. I'll work to get those and I'll send those out. Hopefully we'll be able to be up in the same place we were. So again, as usual, an opportunity for you all to come and ask any questions that you may want before the exam. So let's go ahead and finish up chapter 8. This is, I think, where we left off, where we were talking about some interesting ethers. We had talked about interesting alcohols, and now we're moving into ethers. What's interesting about these are called crown ethers. Anybody tell me why we call them a crown ether? Yeah, it looks like a crown. It's pretty obvious, right? So, and in fact, if you were to build a model of a crown ether, it would look like a crown. The little oxygens would be on one side, and you would have this crown. And these are actually interesting molecules because they have a cavity on the inside. If you built a model of it, you'd see a cavity. And things can fit in that cavity. Things like a potassium ion or a lithium ion. And so we use these crown ethers to extract things from natural sources. So for example, if you wanted to get lithium out of a dirty sample, you can use this so-called 12 crown 4. 12 meaning that there are 12 atoms in the ring. 4 meaning 4 oxygens. That's where the name comes from. And it turns out that lithium is just the right size to fit in there, but potassium is not. If you wanted to extract the potassium, you'd have to use this crown ether called 18 crown 6. And so lithium is kind of an important thing these days. Anybody can tell me why lithium is important? Pardon? Batteries. That's right. It's important for other reasons as well. Even medical reasons. Lithium is a prescribed drug. It's lithium carbonate. But having sources of lithium for not only medicine but also batteries, future electric vehicles, your cell phones all have lithium type batteries in. We need sources of lithium ions. This is one way in which you can extract these things from natural brine solutions that they get from the ground, and they can harvest these materials. Okay? But they're ethers. It's just a molecule that has more than one ether, right? So there's an ether, right? There's an ether, so on and so forth. We can prepare alcohols and ethers using SN2 chemistry. We've talked a little bit about this in the past, right, in the last chapter, but we can take alkyl halides. What would the name of that alkyl bromide be right here? How would we name this? How would you name it? 1-bromoethane. That's technically correct, but is it necessary to use the number? Why not? Either side, it would still be 1-bromoethane, right? So bromoethane is just fine, right? We have bromoethane. What kind of alkyl halide is that? Is that a primary, secondary, or tertiary alkyl halide? Okay, we've got a carbon. How many carbons are attached to that carbon? 1, so it's a primary. This is a primary alkyl halide. Very important. It is a primary alkyl halide. We're going to react that with hydroxide, of course sodium or potassium hydroxide. And this is going to be an SN2 mechanism, so the reaction is going to proceed. How would I push the arrows? Where would I start? the hydroxide, right? And I'm going to draw an arrow to where? I'm going to draw to the carbon from the back side, right? And I'm going to break that carbon-bromine bond. That's an SN2 reaction, right? Notice there's no heat, because we also have to pay attention to elimination. We learned about that, right? So this is low heat. It's a primary alkyl halide. This should go through an SN2 mechanism, and in fact it does. So we can make alcohols this way, right? So you could take bromoethane, you can react it with hydroxide, and you can make ethanol. You can make essentially what's called grain alcohol. This would be an extraordinarily expensive way to do it. Nobody does it this way, at least industrially, but it's possible. We can also make ethers this way, where we take an alkyl halide and what's called an alkoxide. Okay, so this was hydroxide for the hydrogen. This has an alkyl group attached to the oxygen, so alkoxide. Same type of mechanism, right? How would you name that alkyl halide? What's our parent? Propyl. Okay, so propane, right? 1-chloropropane is the number important here. It is, and why? So I could also have 2-chloropropane, couldn't I? Right, so we have to have it there. So this is 1-chloropropane. I'm reacting it with the so-called alkoxide, or methoxide as they call it, because it's a methyl. This is an SN2 reaction too. So notice the reaction mechanism is exactly the same. But instead of getting an alcohol, I'm getting a ether. This is called an unsymmetrical ether. Why? Because if I look at the oxygen, I've got two different alkyl groups attached to it. A methyl group and a propyl group. Okay? We can also prepare symmetrical ethers. I'm not going to go through it, but in this case, if I took ethyl or bromoethane plus ethoxide, notice the alkyl groups on both species are the same number of carbons. I get what's called a symmetrical ether. Okay, and in that case, you get, when I draw it out, that's my favorite molecule during the Halloween season. Can anybody tell me why? Looks like a bat, right? Or a seagull. Some people call it a seagull. But when you draw in the lone pairs of electrons, I think it looks like a bat. So it's always my favorite molecule during the Halloween season is diethyl ether. And so that's what you just made there. Preparing ethers through this process is a named reaction. We will not focus an awful lot on named reactions in this class, but if you take the regular organic 1 and organic 2, you'll be named reaction to death. There's all kinds of named reactions. But this is an important one. This is called the Williamson ether synthesis. So if you ever come into an organic chemistry laboratory and you walked in and you were talking with your professor, they wouldn't come in and say, you know, I think today we're going to take ethyl bromide and react it with ethoxide and make diethyl ether. They would say, Alyssa, I want you to go do a Williamson ether synthesis. That's how we talk. We talk based on named reactions. Okay, so there's a lot of named reactions. The Williamson ether synthesis, Grignard reaction, yada, yada, yada. We'll use a few of them in this class, but not many. In fact, if you ever intend to go to graduate school in chemistry, you will probably take a class where you learn a bunch of named reactions, because it is the way in which organic chemists talk. All right. We can also prepare alcohols by the hydration of an alkene. I can take an alkene and I can add water across the carbon-carbon double bond. We've already talked about that a little bit in a previous chapter, right? So I can take an alkene, I can take an acid. This is just a generic form of acid, right? So remember, anytime you add a strong acid to water, you make H3O+, right? And so what happens in this first step is that the alkene gets protonated. So the carbon-carbon double bond breaks, picks up a hydrogen, water functions as a leaving group, and I get a carbocation. Okay? We've already talked a little bit about this. I've got a carbocation and now I have water. Is a carbocation stable? I'm seeing people shake their head this way. That is correct. It is not. It's an intermediate. It's a highly reactive intermediate. It does not have an octet of electrons. And so it will react with just about anything that has a pair of electrons, right? What has a pair of electrons there? It's not explicitly written. That oxygen on water, right? And so now the water attacks the carbocation. That's a fast step. And you get this carbon-oxygen bond. Notice now the oxygen is positively charged. Oxygen's neutral, reacts with something that's positively charged. It becomes positively charged. We've got to have balance on both sides. These intermediates are called oxonium ions. Alcohols like to form oxonium ions, okay? And so this is nothing more than a protonated alcohol. And so what happens in this reaction is another molecule of water comes in and deprotonates the alcohol, and you end up forming the alcohol and you get your acid back, okay? So I hate trying to point it here. I started with acid and I get acid back. What does that tell us about what role does the acid play? Do you need a lot of acid for this reaction? Let me ask you that. You're saying no. You're saying it correct. Why not? There's already acid, and I'm getting the acid back, aren't I? Am I ever really using up the acid? No. This is a catalytic reaction. I only need a catalytic amount of acid. So if I was doing this in the lab, I would take my alkene, I would somehow get it to mix with the water. We won't go into that. And then I would add just maybe a milliliter or two of concentrated sulfuric acid to the reaction mixture and let this go and make the alcohol, okay? So we can hydrate alkenes. What would I need to be careful about here? What did we learn about carbocations? They're very reactive. And what else?
They'll react in any way that'll make them stable.
They will react in any way that will make them more stable. Good. And what did we call that? Rearrangement. Remember, a carbocation can rearrange to a more stable carbocation. And that doesn't change here. Anytime you have a carbocation, I don't care what you generated it or why you generated it. If it can rearrange to a more stable one, it will. It just so happens in this particular example, there's no way for it to rearrange to a more stable carbocation, so nothing happens. But that's not always the case, right? So let's look at this example. I want you and your partner, your next door neighbor, take a moment and try to figure out what might happen just in the first step of this reaction. And again, you can think of H plus as H3O plus. I don't care how you think about it. It's just acid. So you've got that alkene in the presence of acid. What do y'all think? What do y'all think is going to happen? How would you draw the arrow? Where would you start? Where would we start? We're going to start at the double bond. Why are we going to start at the double bond?
Because they like to break.
Okay, it does like to break. There's no denying that. It likes to break because it's the weaker bond, right? Because of how the orbitals touch each other. But I always like to say because that's where the electrons are. All the other electrons are tucked in between atoms. These are out and above, right? So they're reactive, right? So, yeah, the first step, H plus, I'm going to do that. Which one of these carbons, carbon 1 or carbon 2, is going to get that hydrogen? Carbon 2. So if I do that, let's just do that. If I do that, and put the hydrogen there, that gives me what kind of carbocation? Primary. Is that stable? It's not very stable, right? Okay. Now what happens if I put it on carbon number 1? What kind of carbocation do I get? Secondary. Which one's more stable? This one. Yeah. So you could, on an exam, have said, well, I think it goes to carbon number 1. And if you drew it out and asked yourself, well, what happens if it went to the next one? You could have made the decision, right? Whose rule is this? I think I heard it. Markovnikov's rule. Remember, Markovnikov's rule says that the carbon of the alkene with the most hydrogens gets the hydrogen in this step. All right? So we end up with a secondary carbocation. Is a secondary carbocation the most stable carbocation? No, what's more stable than a secondary? A tertiary. Very good, right? Could I get a tertiary carbocation? What would have to happen? Right? So there's my carbocation. I would start looking at things that are attached to it and ask, can anything rearrange? If one of these hydrogen shifts, I get a primary carbocation. That's not going to be any good, right? But what happens if one of these methyl groups shift? Right? So if this methyl group moves over here, I get what kind of carbocation? Tertiary. Is that more stable? It is. So guess what happens? It happens. Right? So you get the carbocation rearrangement. Okay? This is a very fast reaction. It happens very, very quickly. And you end up with a tertiary carbocation, and then that tertiary carbocation then reacts with the water to form the alcohol. I'm not going to go through all those pieces of the mechanism. Okay? But the hydration of alkenes can be problematic because you go through this carbocation intermediate. So always keep that in mind. Okay? Other reactions that alcohols will undergo is they will react with strong acids, just like water will. You all learned in Gen Chem that if you take a strong acid and you place it into water, that it completely dissociates. Guess what? You take a strong acid and you place it into an alcohol, it will dissociate. Because again, alcohol is nothing more than an organic version of water. It may not dissociate to the same extent. I'm not suggesting that, but it will dissociate. And it will react with the alcohol. So what happens, of course, is that we've got a strong acid. Acids like to react with bases. What's the base here? If HA is the acid, what's the base? The alcohol, the oxygen atom of the alcohol, right? It reacts and we form this oxonium ion. Looky there. Alcohols like to make oxonium ions. These oxonium ions can actually function like leaving groups, and they can participate in SN2 reactions. So for example, I could have a protonated alcohol. It can react with some type of nucleophile to give me a new in this case, I guess carbon-carbon bond plus water. Water is a good leaving group. Okay, and so this happens. So, for example, let's suppose Rose comes into my lab and I ask her to do a reaction that requires 2 bromopropane. So she needs that. She goes into my inventory, she goes and looks, and she comes back to me and she says, "Bad news, boss, we don't have any 2 bromopropane." But she comes back to me and she says, "But we've got 2 propanol. We've got isopropyl alcohol. We've got lots of rubbing alcohol." Okay? So we got a lot of this. And she wants that. How can we do it? I got the right number of carbons. There's 3 carbons. There's 3 carbons. I've got a bond to an oxygen in the position that I want the bond to the bromine. So what can I do? How can I use this chemistry to do that? What do I need to do? What do I need?
Just switch the alcohol with the.
I need to replace that OH with a BR, right? Yeah, that's what I need to do. What can I do to do that? Right? What can I do to do that? What do y'all think? We got to have this molecule tomorrow. What can we do? Can't wait to order it. Takes too long to get it shipped here. We got to have it. How are we going to take what we have and get what we want?
Did you add HBr to the solution?
Could I add HBr to the solution? That's a good hypothesis. Can I add HBr to the solution? Am I causing doubt? Am I causing doubt? Go with it. I just told you we could add strong acids to alcohols and we get these oxonium ions, right? You just picked a strong acid. So what can I do? Yeah, you're right. What can we do? What would happen? Right? If we think about this first reaction.
The BR would replace the OH and the OH would pair with the other H to form H2O.
Yeah. So what happens, right, is we form the oxonium ion. Let's be our minus. Remember, as you go down a family, so fluorine, chlorine, bromine, and iodine, as you go down a family, the nucleophilicity of the atom increases. Bromide is a good nucleophile. Water is a good leaving group. And lo and behold, Rose just made 2 bromopropane. And now we can give it to Barrett and he can go do whatever we need him to do. Right? So this reaction works very, very well. In fact, you can take alcohols and you can do this chemistry quite nicely. Very, very easily, in fact. This is soluble in water. This is soluble in water. Do you think this is soluble in water? It is not. Alkyl halides are typically not soluble in water. The reaction is so easy to do, anybody can do it. You literally take the alcohol, you put it in a funnel, the separatory funnel. Have you all seen the separatory funnel in the lab yet? Thing that you shake, separates layers. Haven't done that yet? Okay, so anyway, it's a simple piece of equipment. It's kind of cone shaped. It's got a little stopper at the top, you can shake things. You take that, you put it in the funnel. HBr comes in water, so you add that. and it all looks like it mixes together. You shake it up and you set it, and all of a sudden you start to see another phase form. And that's this. The reaction happens and this floats to the top. You simply drain off the lower water stuff, you keep the stuff that's on top, and you're done. The reaction takes literally 5 minutes, and you're done. That's why I'm not going to order it and have it delivered in. We can just make it in 5 minutes and move on to the next step. These things happen very, very easily because of this type of chemistry. Okay? So, we can convert alcohols into alkyl halides. We can take what we're learning in Chapter 8 and apply it to Chapter 7. Right? We just talked about alkyl halides. We just learned that we can take alkyl halides and make alcohols, but guess what? We can also take alcohols and make alkyl halides. We can do the reverse, okay? So this is a very common thing that happens in the organic lab. And so you'll find that HBr works really well, HI works really well, and even HCl will work. What is absent? HF. HF does not do this. And in fact, you will probably never work with HF. It is a nasty little molecule. But it doesn't do this chemistry, okay? But there are other reagents that also do this. You're not limited to these types of reagents. Phosphorus halides work. So PCl3 or PBr3 or PI3. And thionyl chloride, SOCl2. These reagents will all convert an alcohol into an alkyl halide. So if I take isopropanol and I react it with SOCl2, what's the alkyl halide I'm going to get? What am I going to get? What am I going to get? Play molecular hangman here. Give me the 3 carbons. What do I have to put on? Think about the general reaction. OH gets replaced with what? It gets replaced with what? X, a halogen, right? What's the halogen here? Chlorine. Yeah, that's the only halogen I've got. I don't even have to worry about the mechanism. I know that that's what's going to happen because of what the general reaction mechanism is, right? So if I do that, I can also what's the product of that? It too is the chlorine, right? What's the product of this one? Chlorine again, right? 3 different ways to get to the same product. Why do I need 3 different ways to get to the same product? Because thionyl chloride is very reactive. Maybe I've got something else that will also react with thionyl chloride, so I can't use that method. Maybe I use PCl3 or HCl, right? There are a lot of reagents that can kind of do the same thing. Okay? That's the kind of important thing. But in commonly, I should say, hydrogen halides or HX are what most people use if they can get away with it. Why? Because it's cheap. I got a bottle of hydrochloric acid. I got a bottle of hydrobromic acid. Okay? Works pretty well. And so, here are some examples of ways in which you can convert an alcohol into an alkyl halide. We have not talked about all of these things that you're seeing over the arrows yet, but I want you to take 5 minutes and work with your partners, and I want you to figure out what each and every one of the products from those reactions is going to be. Even though we haven't talked about everything that's over those arrows, you know enough now to where you should be able to predict what the product's going to be. Take a moment. There is a word up there that I would let you all know. If you haven't heard the word reflux, it means to boil. You all have heard of acid reflux? Kind of the same thing. What's going to happen in the first reaction? We're going to what? We're going to replace OH with Br. Yeah, makes sense. How would you name that alcohol, right? They say it's butyl alcohol, but how would you name it? One butanol. Yeah, that would be the more appropriate name that you all would probably come up with, would be 1-butanol. But butyl alcohol is a common name. And this is using HBr gas. It says up there at the top, dry HBr gas. You can generate HBr gas pretty easily. You can also make HBr gas by taking sodium bromide and sulfuric acid. It actually makes HBr gas. HBr gas is kind of a brownish color, really, when you make it, and so you can see it get made pretty easily. So that's really what these conditions are. Reflux means to heat this up and boil it. So basically what we're doing is we're taking the alcohol, we're bubbling HBr gas through it, and we're heating it up. And what we're going to do is we're going to get 1-bromobutane. Okay? What's the mechanism? Is it SN1 or SN2? Is it SN1 or SN2? 1 or 2? Kind of sound like I'm at the eye doctor. 1 or 2? It is SN2, right? And why is it SN2, Baron?
Because I was thinking like from the reverse where it goes from bromine leaving to form the alcohol, it would be a primary carbocation. Those favor SN2 over SN1.
Okay. So in the first step, you're going to protonate the alcohol.
Right.
And then the bromide's going to come in an SN2 reaction and kick out. We can't have a primary carbocation. So, yeah, makes sense, right? Now we take this propyl alcohol, and you all would name that how? 1-propanol. Okay, good. And they take HCl. Then they add this stuff called zinc chloride, and then they reflux it. And what's the product going to be? Yeah. Is that SN1 or SN2? If it's SN1, I'm going to go through a carbocation. Do you think I'm going to get a carbocation if this leaves? That didn't give me a primary carbocation, right? So probably not going to do that. So this again is an SN2 reaction. Okay? Why didn't they just use HCl in reflux? Anybody want to take a guess? Why did they add zinc chloride?
Is it a catalyst?
It's not technically a catalyst, but it serves the same purpose. It does get used up in the reaction. That's why I'm saying it's not a catalyst. But catalysts speed up reactions, right? This also speeds up the reaction. When you take HCl and you mix it with zinc chloride, this is called Lucas reagent. Don't worry about writing that down. But these are both SN2 reactions, which means that the chloride has to come in from the back and kick out the leaving group, right? Well, that's the same as HBr. Why didn't we add zinc bromide up here? Okay, what is it better?
Works faster.
Okay, that's true. Bromide, remember in the family, fluorine, chlorine, bromine. Bromine or bromide is a better nucleophile than chloride. So this is a really good, bromide is a really good nucleophile. Chloride is not. And so we've got to kick it in the pants a little bit and use some zinc. Okay? That helps remove or make that alcohol a better leaving group so that the chloride can function as a nucleophile. What about the third example? Taking tert-butanol and HCl at room temperature. What's the product we're going to get there? Tert-butyl chloride. Okay? Is that going to be SN1 or SN2? One or two. Do you think once this gets protonated that the chloride can come in from the back and kick out the leaving group? It's got a lot of stuff around it, doesn't it? Can't do it. So this is going to be SN1. It goes through a carbocation mechanism. This is how we make tert-butyl chloride in my lab. I refuse to buy this stuff because I've got gallons of tert-butanol. You literally pour some in a separatory funnel, you put an equal volume of concentrated hydrochloric acid, you shake it, you set it down, you wait for 4 or 5 minutes, it separates out, you've got your pure tert-butyl chloride. Okay? I just use what I got. I get this pure, don't have to worry about it. So yeah, we get these products quite easily from this type of reaction. Another reaction that alcohols like to do is called dehydration. What do you think that means? Eliminate water. You all have been dehydrated, I'm sure, at some point, right? You're out in the hot sun, you start to get a headache, you go, I'm dehydrated, I need to drink some water. Same thing happens to alcohols. You can remove water from alcohols, and you can form, what do you think you form? Alkenes. It is exactly the opposite of hydration. We just learned that I can take an alkene and I can add water to get an alcohol. I can do exactly the opposite. I can take an alcohol, I can remove the water, and I can get an alkene. Okay? This is a beta elimination. Here are some examples. Notice the acids that are being used. For the purposes of this course, we're only going to talk about one dehydrating acid. There are several, but it's sulfuric acid. Sulfuric acid is called a dehydrating acid. It likes to remove water from carbohydrates and alcohols. Okay? If you're ever in the lab and you're working with sulfuric acid and you get a little bit on your clothes, the next day when you wash your clothes, you will see a big hole where that spill occurred because it dehydrated the cotton and made it weak. And then when you washed it, it falls apart. Okay, so I used to work in an environmental laboratory. That's how I paid my way through college when I was in your boat. I worked for an environmental laboratory, and we had to do a lot of stuff with sulfuric acid, and I had to kind of wear not fairly nice clothes, not Sunday best or anything, but fairly nice clothes. And it was, my wife would always know when I'd been working with sulfuric acid because there would be little prickly holes all in my shirts and stuff like that. And then she would get mad at me for not wearing my lab coat. Okay? So it's important to wear your lab coat. Okay? But notice what's happening. We can take ethanol, we can take a little sulfuric acid, we can heat this up, we can get ethylene. Okay? This is how you would get ethylene, or ethene, as you probably would name it, to make polymers from biomass. You would convert the biomass into ethanol, you would then dehydrate the ethanol to get the ethylene, you would then polymerize the ethylene to make whatever plastic you wanted to make with it. Okay? You could do that. You can also take cyclohexanol, react it with sulfuric acid, heat it up at about 140 degrees, you can get cyclohexene. Okay? You can take terpbutanol. You can just warm it up slightly with sulfuric acid and you can get so-called isobutylene or 2-methylpropene. Okay? These are all dehydrations. If you're interested in something that's a little more exciting than what I'm showing up here, go on YouTube and type in something like sugar and sulfuric acid. You can take a bunch of sugar cubes and stack them up, and you can pour concentrated sulfuric acid on it, and it will start to form this snake of black char that will come up, and it will be steaming. The steam that's coming off is the water from the dehydration, and what is left is pure carbon. Sugar is nothing more than a bunch of alcohol groups. It's a carbohydrate. It's carbon plus water. That's all sugars are, okay? Or just pure carbon and pure water mixed together over time, right? And you can see that. That's a dehydration reaction. All right. Let's talk a little bit about some mechanisms of dehydration. Help walk me through what you think the mechanism is going to be. What do you think the first step is going to be? How do you look at these reagents and think about how they behave? What do we know about sulfuric acid?
It's going to remove the alcohol.
We know it's going to remove the alcohol. We know it's a dehydrating acid. We also know that it's a strong acid, correct? What happens to strong acids when you place them into solution? They dissociate. So when I see sulfuric acid, and this isn't technically correct all the time, but it works. I always think of sulfuric acid as H plus and HSO4 minus. That's how I visually think about sulfuric acid. So I've got a Lewis acid and I've got a Lewis base. So the reaction happens. This is perfectly reversible. Now what do you suppose happens?
It's going to be a double bond that forms.
We'll get a double bond that forms somehow.
The water will be,
And water will be a product. Yeah, we're going to remove the water. Do I have an issue here that I have to think about though? right? This is my alpha carbon, right? This is a beta elimination. I've got beta 1 and I've got beta 2. Which beta carbon gives up its hydrogen and why? Is it beta 1 or is it beta 2? Whose rule is that we talked about? Zaitsev's rule. What does Zaitsev's rule say?
That the beta carbon with the less hydrogen will give up one.
All right, so we know we're going to lose the hydrogen from beta 2 and we're going to get that product. Now, how in the world does that happen? How in the world does that happen? Well, I've got 2 hydrogens on beta 2. I've got HSO4 minus. It happens just like that. I get my sulfuric acid back. And this is reversible too. Right? Because we learned that we can take an alkene plus sulfuric acid and water and we can make an alcohol. So how does Baron take this alcohol and make it go all the way to this without going back? Whose principle does he use? Zaitsev is a rule. Markovnikov is a rule. But there's a principle that you might have learned in Gen Chem called Le Chatelier's principle. What does Le Chatelier's principle tell us? Le Chatelier's principle tells us that we can drive an equilibrium reaction one way or the other if we play with some things, right? This boils at a pretty low temperature. So maybe I just boil this out, heat it up a little bit and let this come out of the solution. That would drive the reaction this way. Or I got to have water around for it to go backwards, right? So maybe I have something that removes the water from the reaction mixture. That can make this go this way, okay? So we can play with what's called Le Chatelier's principle. So when you have something in balance, in equilibrium, if you tip the scale on one side, it affects the other, right? And so we can do that through this thing called Le Chatelier's principle. That's really all we're going to cover in terms of the mechanism for this particular reaction.
Does that mechanism have a name?
Does the mechanism have a name? It does not. It is not a named reaction, no. Not to my knowledge, anyway. All right. You all need to be able to calculate the oxidation states of alcohols. It's something that you're going to have to be able to do on an exam. I will give you a problem where I give you an alcohol or something like it and say, what's the oxidation state of the carbon? There is a difference between calculating an oxidation state and calculating formal charge, but they're similar. When we calculated formal charge, we assumed that electrons were equally shared. Oxidation state, you do not assume that the electrons are equally shared in a bond. Okay? That's the big difference. And so it's really going to be, again, simply taking the valence electrons for the atom and subtracting from it the assigned electrons to get the oxidation state. Okay? So here's an example of an alcohol. How would we name this alcohol? It's my favorite alcohol. How many carbons are there? 2. So this is ethanol. We're going to calculate the oxidation state of this carbon in ethanol. Okay? So, when I look at this carbon-oxygen bond, what's more electronegative, carbon or oxygen?
Oxygen.
Oxygen. So all of these electrons are formally going to be assigned to oxygen. You always assign the electrons to the more electronegative atom. Okay? What's more electronegative, carbon or hydrogen? Carbon. So we're going to assign those electrons to carbon. We're going to, in both of them, What about when I have a carbon-carbon bond? They have equal electronegativity, so we assign one electron of the bond. Okay? So, I've got no electrons here. I've got one electron here. I've got 2 and 2. So 2, 2, and 1 is 5. The oxidation state for that carbon is 4 minus 5, it's minus 1. That carbon atom is in the minus 1 oxidation state. Okay? It was oxidized to a minus 1. Take a moment with your friends and calculate the oxidation state for the carbon in methanol and for the carbon in formic acid. How do we calculate the oxidation state for methanol? What do we do? Where do we start? Find the electrons. I know it comes in with how many? 4. And I'm going to subtract from that the number that are assigned to it, right? How many are assigned from this bond? What's more electronegative? So does carbon get any? No. I'm just going to, doesn't get any. How about these? What's more electronegative, carbon or hydrogen? Carbon, so it's going to get these two, and these two, right? It's going to get 6. So 4 minus 2 is always, or excuse me, 4 minus 6 is negative 2. This has a different oxidation state than ethanol. And you might have looked at it initially and said, well, it's going to have the same oxidation state as ethanol. It's a primary alcohol. But it's not. It has an extra hydrogen. It makes a difference. All right, how about for formic acid? It comes in with 4. We're going to subtract from it the number it formerly owns. Does it own any of these? Does it own any of these? Does it own any of these? Did we get it right? We did. Simple arithmetic. Okay? What do you all know about formic acid, just to see if you might know a little trivia here? Pardon? What might you know about formic acid? Have you ever been walking out in your yard and stepped into those little mounds of fire ants and gotten bitten? What do you think they injected you with? Formic acid. That's what they injected you with. One of the things that they inject you with. Okay? It is something that the acids make. And in fact, interesting little piece of trivia, useless trivia. 110, 150 years ago, something like that, if you wanted formic acid, you literally went out and harvested ants and you distilled them. You put them in a big flask and you heated them up until they burst open and you distilled out the formic acid. Poor little ants, right? Today they're such a nuisance, I'd really like to try it. But I don't have the time to go dig up a bunch of ants. I can only imagine that it took trillions of ants to do that, okay? So it turns out that alcohols can be oxidized, okay? This is an important thing to know, okay? So alcohols can be oxidized and they can form other functional groups. So for example, if the alcohol, if the carbon containing the OH has hydrogens on it, you can actually oxidize that to a new functional group, right? I can take a primary alcohol, for example, and I can oxidize it. O in bracket means oxidation. We don't know what the reagent is yet, okay? It's just a general term for oxidation. And I can either convert this into an aldehyde or I can convert it into a carboxylic acid. There's two possibilities, depending on the reagent that I use. But if you calculate the oxidation state for this versus these, you will see that it's actually undergone oxidation. They've lost electrons, okay? So you can get aldehydes and carboxylic acids by oxidizing primary alcohols. If you are a wine aficionado, what is one of the big enemies of wine? Oxygen, air. Air contains oxygen. If you let wine sit out for a very long time, it oxidizes and it turns to vinegar, carboxylic acid. Okay? Wine, the alcoholic component is ethanol. It's a primary alcohol. It does form the aldehyde in the air, and then that oxidizes further over time to make the vinegar, the carboxylic acid. Okay? That's why people who really, I mean, I like wine, but I don't collect wine or anything like that. But people who collect wines, very valuable wines, will actually take the bottles in and have the corks inspected. Because you don't want air getting back into there, or that $1,000 bottle of wine you bought all of a sudden becomes a $10 bottle of vinegar. Air is an enemy. It's oxidation here. Secondary alcohols have one hydrogen bond on the carbon containing the OH. They can only form one type of product, and that is a ketone. You can oxidize secondary alcohols into ketones. If you go home tonight and you read on your isopropyl alcohol bottle, it will have an expiration date. Believe it or not. It has that expiration date because it will react with oxygen over time to form acetone, a ketone. Okay? It's a very slow reaction. Most of you go through your alcohol way too fast for that to ever really be a problem. But if you kept it around for a dozen years or so, and you went and smelled it later, you'd probably smell a hint of fingernail polish remover in it. You'd be like, did somebody pour fingernail polish remover in this? No, it just oxidized, and it formed a little bit of acetone. Okay? Tertiary alcohols, however, have no carbon-hydrogen bond. And so they can't undergo oxidation. I can take a tertiary alcohol, I can leave it out in the air for a long time. It will not oxidize to anything. Okay? They do not do a reaction to form another functional group. Okay? There are a couple of reagents that you need to know for the purpose of this class. Okay? Notice the common thing in all of these formulas up here. What's common among all of them? Two things.
CRO.
Chromium, Cr, and oxygen. Anytime you see Cr and O together, you can think of that as an oxidizing agent. It will oxidize an alcohol into something. Okay? And so you can use chromium trioxide, you can use sodium dichromate, you can use potassium dichromate, and you can mix those in a strong acid, usually sulfuric acid and water, and you can use this to oxidize alcohols. Okay? Collectively, this group of things, when you take chromium, any of these, and dissolve them in sulfuric acid and water, we call this Jones reagent. Okay, so again, if Rose was coming to my lab and wanted to oxidize an alcohol, I'd say, go get the bottle of Jones reagent. I wouldn't say, go get the bottle of chromium dioxide or chromium trioxide, sulfuric acid, and water. I'd say, go get the bottle of Jones reagent. Okay? And so that works really well. The other reagent you need to know is called PCC, pyridinium chlorochromate, PCC. It is another reagent that will oxidize alcohols to other things. And you need two different types for a reason, and we'll go through that in just a moment. PCC is soluble in things like dichloromethane and good solvents. Chromium trioxide and all this stuff isn't. It's really only soluble in water, and that makes a difference. But what is the same between them is that chromium in both cases is in the same oxidation state. These are chromium plus 6. What color might you think chromium plus 6 is? Blue? Think blue? Must be your favorite color, huh?
Yellow,
It's my favorite color. No? What'd you say?
orange.
Orange. Yeah, it is orange in fact. Okay? And it looks kind of like this. That's chromium trioxide and sulfuric acid. Nice orange color. Okay? Now, if you take a primary alcohol and you react it with PCC, it will only give you the aldehyde. It stops at the aldehyde as long as there's no water around. It'll stop at the aldehyde. If, however, I take that same primary alcohol and I use Jones reagent, it will give me the carboxylic acid. That's why we need two reagents. Maybe Rose wants to make the aldehyde. She's going to use PCC. Maybe Alyssa wants to make the carboxylic acid. She's going to use Jones reagent. Okay? So you can oxidize things through these choices of reagents very, very easily. Okay? This has practical applications. Back in the day, there were these things called breath scan. I don't know if they still have them or not. This was back in the 1980s. I remember them. Mothers Against Drunk Drivers, MAD, came out trying to reduce the number of drunk driving fatalities. And they would go to parties and pass out these breath scans. So if you were leaving a party, and the whole thing was, we're not judging you as parents, we know kids drink. Here's a breath scan, make sure you're driving safe. They'd give them to kids. You would breathe through it, and it would start out this orange color. It's chromium trioxide, it's orange. Okay, and you would breathe through this tube into a balloon kind of looking thing. And as you would breathe, if you had a lot of alcohol on your breath, it would start to turn green. Because if you're oxidizing an alcohol, you have to be reducing something else. And what's getting reduced? The chromium. Chromium in the 3+ oxidation state is green. And so the further the green moved up the tube, the drunker you were. Okay? And there was a magic line somewhere that said if it turned past this, that you were not safe to drive. And that's what you did. Right? So people would take these, you would breathe through them for a period of time, you would then look to see how green it turned, and you would determine whether or not it was safe to drive. Okay? We no longer use these breath scans as far as I know. Can anybody tell me why? Two reasons. Number one, we have electronic versions of this that work a lot better. And two, chromium is a very potent environmental hazard. So what do you think people did at a party when they were done with these? You think they disposed of them properly? No, they pitched them out the car window and drove off, right? And put chromium in the environment. Not a good idea. But nonetheless, it works. I mean, it does work. And in fact, here's an example. So I took this picture a long time ago. You can see by the date. But here's Jones reagent. You can see the nice orange color, right? And then what I did was I took a few drops of absolute ethyl alcohol, 200 proof, and I dripped into another dish of this. And you can clearly see it's green, right? So as I was oxidizing the alcohol, I was reducing the chromium. So it went from chromium in the +6 oxidation state to chromium in the +3 oxidation state. It's less plus. It's more reduced. And reduced chromium is green. Okay? And so what happens is I take the ethanol and I make vinegar out of it. Acetic acid. Pretty easy. This turns out to be important biologically. This is what your body does when you go have a drink. Your liver has P450 oxidation enzymes. It is your biological equivalent to chromium trioxide. I can't put chromium trioxide in a biological system, it'll kill you. But P450 enzymes are fine. Okay? So, I'm at the bar, I take a drink. What's happening is, as it gets through the body, it goes into the liver. The alcohol first gets converted to what's called acetaldehyde. It gets converted to the aldehyde by the enzyme. And then over time, it gets converted into the carboxylic acid, okay? Now, they say acetate here because the pH of your bloodstream is such that it wouldn't be in acidic form, it'd be deprotonated, okay? But this little guy right here, acetaldehyde, is why you experience a hangover, okay? It's very toxic. Aldehydes are typically quite toxic, okay? And so as you ingest the ethanol, that's what happens. But your liver can't tell the difference between ethanol and methanol. It will oxidize both of them. And so if you happen to be unfortunate and you bought hooch from a bad distributor who gave you the heads that contains all the methanol and you drank it, what would happen first is the alcohol dehydrogenase, or the P450 enzyme in your liver, would oxidize this to formaldehyde. And then formaldehyde gets further oxidized to formic acid. Okay? What do you all know about formaldehyde from your general biology classes in high school? It's a preservative. What do you think preserve means? Living or dead? Dead. Right? You put frogs in formaldehyde to keep their dead bodies from decomposing. So what do you think happens if you ingest methanol? You eventually die if you drink about 100 milliliters of it. But only 15 milliliters, which is about that much. Right? If you took a shot of methanol, you would go blind. And the reason is because of the formaldehyde. The formaldehyde will react with your optic nerve, and it's irreversible in this particular case. And you will go blind. You will have essentially pickled your eyes. You would have preserved them. You've preserved them, but they can't see anything, right? So I'd much rather have my unpreserved eyes that I can see with, right? So, that's it for today. So, I didn't have time to get to the file stuff, so we will cover that on Monday. So the good news is you're off the hook for a quiz on Monday. Right?
Yes.
But you do have a quiz coming up on Thursday, so it's still in your best interest to make sure you work the problems. So you shouldn't be working problems just for the quizzes, right? So for today, I need you to turn in problem. Let's turn in problem 722, 7.22.